Shall we begin then? So yesterday we looked at this pair of wells that were separated by a barrier so that classically the particle couldn't get from one well to the other, and we found that the particle got from one well to the other and used that to make a model of an ammonia maser with a nitrogen atom passing through the barrier formed by the hydrogen atoms. So let's look at this phenomenon from another perspective, from the perspective of a scattering experiment. And we'll come on to what this has to do with radioactivity, I hope, at the end. So consider this setup. We have a potential barrier here of height V0, usual square form for computational convenience. And we have some incoming stream of particles. We have a beam of particles here represented by the wave function a plus e to the ikx. So these are, of course, particles with well-defined momentum approaching the barrier. We expect to see some of these particles reflected. Classically, if the energy of these incoming particles were less than V0, they would all be reflected. So we put in a reflected wave here, which goes like e to the minus ikx. Remember, the time dependence of everything in quantum mechanics, for a state of well-defined energy, is e to the minus ie upon h bar t. So these things have sort of e to the minus I omega t type dependence, and therefore if you have a minus sign here, you're looking at a wave which is traveling to the left. If you have a plus sign here, you're looking at a wave which is traveling to the right. And then we expect some of the particles to get through, so we put in a wave in this portion. We say the trial solution should look like C with some unknown constant C, e to the ikx. And then within the barrier, because we're going to look for solutions at energies lower than V0, we're going to have B plus e to the kx plus. The trial solution will be a combination of an exponential growth and an exponential decay. So this is a more complicated, so this is a bit different from what we've done before in two ways. One is that, well, the main thing is that our problem inherently has a lack of left-right symmetry, right? The potential that we're discussing here has left-right symmetry. It's symmetrical around the origin, which I forgot to say, but the origin is here in the middle of the well. This is minus A, and this is A over here. So the potential is going to be an even function of x, same as ever. But our problem, our initial conditions, the physical situation we wish to discuss has a built-in asymmetry because the particles have to come in from one side or the other. Now that is computationally very inconvenient. It stops us using this nice trick. It makes it difficult for us to use this nice trick of looking for solutions to the problem which have well-defined parity, and thus discussing only what happens at this boundary condition. With this setup, we're going to have to discuss this boundary condition and this boundary condition because you can see there are fundamental differences between what's happening on those two sides. Now, you can handle this problem using looking for solutions of well-defined parity, but it's slightly unnatural, and I think, well, it's actually a very good way to go, but it's not such an obvious and intuitive way to go, even though it's computationally simpler. And I think it's worthwhile just seeing what happens when you play the game straightforwardly, and you'll see the algebra becomes quite unpleasant, which illustrates the benefits that we had before by assuming well-defined parity. All right. The other thing that's different here is that because we are considering particles which are free, because the potential goes to zero outside this interval here, the particles, and we're going to consider particles with positive energy, the particles are going to be able to push off to infinity, so we're not going to find discrete energy levels. We're going to be able to find solutions for any energy, right? Whereas previously we had a potential which forbade going to infinity, and that made the energy levels discrete. So those are the differences, because we're dealing with a different physical situation, and it has implications for the maths. Right, so what do we have to do? Well, it's very boring. We have to impose continuity of the wave function. So the wave function here is this wave plus this wave. And that has to be continuous at this boundary x equals a. So it has to give you the same numerical value as the sum of these two things here. So let's just quickly write that down. So we have a plus e to the minus I k a, which is the incoming wave evaluated at that barrier, x equals minus a, plus a minus e to the plus I k a. And that had better equal b plus e to the minus k a. Plus b minus e to the minus, no, that one's got plus ka, right? Many double negatives here, unfortunately. I forgot to say, of course, that we'll have as ever that k is equal to the square root of 2m times the energy over h bar squared, because p squared over 2m is the energy and p is h bar squared k squared. Sorry, p is h bar k. And we will have that big K is equal to the square root of 2m v0 minus e over h bar squared. So this is the condition for the wave function to be continuous at x equals minus a. We require, as yesterday, that the gradient of the wave function is also continuous there. So we have to take the gradient of that function on the left and evaluate it at x equals minus a, and we find that ik, common factor, a plus e to the minus ika minus a minus e to the ika, close brackets, is equal to big K, common factor, b plus e to the minus ka minus b minus e to the ka, close brackets. Then we have, so it's two equations. Now we have two more equations because we have to get everything honky-dory on the right-hand boundary, which is not now dealt with by symmetry as it was yesterday. So this is where everything becomes difficult. So we have c e to the ika is equal to b plus e to the ka plus b minus e to the minus ka. And we have that ik over k, I'll write it thus, of c e to the, well, maybe I should leave that one alone, c e to the ika, that's the gradient on the right side, is equal to big K, common factor, open brackets, b plus e to the ka minus b minus e to the minus ka, close bracket, and I live in hope and some anxiety that those equations have been correctly stated. So what do we have to do? We now have 4 equations and 5 unknowns, I think, right? There are 2 A's, 2 B's, and a C. So we will not be able to get rid of all of them. We will be able to express in principle any one of the A, B's, and C's in terms of the other one, and that physically corresponds to the point that the flux of incoming particles is controlled by A plus, and that's in your control. You can put in more particles or fewer particles, and that will obviously lead to more particles coming out or fewer particles coming out, depending on the incoming flux. So the general idea is you expect to be able, the goal is to express any one of these things as a function of A plus, as a multiple of A plus, and we expect them to be linear in A plus. So that's why we've got too few equations. We don't physically expect to be able to determine everything. So what we should do is engage in an elimination exercise. A reasonable way to go is to take these 2 equations here, divide this equation by this equation, say, and that will get rid of C, and will give you a relationship between B plus and B minus. And then you can take that relationship between B plus and B minus and use it in these 2 equations to express the right, to get rid of B minus from these equations, these 2 right-hand sides. So they both become simple multiples of B plus. And then you could divide these two equations one by another. The B plus, which will be a common factor on the right-hand side, will go away. And you will be left with a relationship between A plus and A minus, a single relationship between A plus and A minus. So that will be the promised relationship that expresses the number of reflected particles as a multiple of the number of incident particles. So once you've found what A minus is in terms of A plus, you can go back to your original expression here, which had only B plus on the right-hand side. A minus can be expressed as a function of A plus, and you'll be able to find what B plus is. You'll be able to find what B minus is, and they can all be determined. So let me not do all that algebra. That's the strategy. The execution, of course, is quite tedious, and the scope for making errors is quite large. And in fact, I find that there's a typo right there in equation 540 in the book, because when you do eliminate between these two equations here to find out the relationship between B minus and B plus, it should be that B minus is 1 minus ik over k over 1 plus ik over k e to the 2 big Ka B plus. So that differs from what's in the book, partly by arrangement of this, but more importantly by this having been left out. That's got slipped out in doing the typesetting. Okay, so we have that relationship there. We stuff this back into the other places, and we find that A minus is equal to A plus. So I've described what we do. We take this B minus, use it to get rid of B minus from here and replace that with B plus and some factor. Then we divide these two equations, and then we get this relationship I'm about to write down between A minus and A plus. And it is A minus is A plus e to the minus 2 Ka q minus 1 over q plus 1, where q is itself pretty yucky. It's cosh 2 Ka minus I k on k hyperbolic shine of 2 Ka all over cosh 2 Ka minus big K over Ik of shine. So the algebra is, as promised, altogether more messy than it was yesterday, because we're not exploiting parity. We're not dealing with finding a... Right, so what do we want to know about this physically? What we want to know about this physically, I think, is what is the chance that the particle is reflected? What is the chance that the particle gets through? So classically, everything will be reflected, and the modulus of A minus would be the same as the modulus of A plus, right? And you can see that that isn't looking very promising, because that would require that, well, basically the Q is simply enormous, right? If Q were very large, then Q minus 1 would be the same as Q plus 1, and everything would be reflected. But in reality, it's not all going to be reflected. Something's going to get through. How to find C? Well, you could take this A minus expression, from it, as I've described, obtain B plus, from B plus obtain B minus, to put these back into this equation here, say, and find C. That's too much like hard work. It's easier to say that, look, there's going to be conservation of particles. We've got a well-defined theoretical apparatus here, which is not going to, which conserves probability. So the incoming particles, the A plus, are all going to go out at the end of the day, either to the left or to the right. So we can argue that A plus mod squared, which is, well, that is the spatial density of incoming particles, if you like. If you multiply that by the speed of the incoming particles, which is P over M, so h bar k over M, you will get the flux of incoming particles. And the flux of incoming particles has to equal the flux of the outgoing particles, which is A minus square, the mod square of A minus, the density of outgoing particles, again, times h bar k over m for the speed, plus c mod squared, right? So conservation of particles implies this relationship between these amplitudes. And of course, you can in principle check whether this algebraic relationship is satisfied by these equations by hard slog, because I've described how you can in fact find C. We've already found A minus. You could in fact, in principle, find C and check that it satisfied this equation, but we don't want to do all that algebra. So the point is that what we want to say is the flux of, well, what we want to say is the following, actually, is the fraction of particles that get through is obviously the ratio of the incoming flux and the ratio of the outgoing flux to the incoming flux. So it's going to be this fraction that we want, we'll call it F, is going to be mod C squared over A plus squared. Because the constants of proportionality, namely h bar k over m between this quantity and the outgoing flux on the right, is the same as the constant of proportionality between this constant and the incoming flux on the left. So the fraction of particles that get through will be given by this ratio here, which, given that relationship, so in other words, C, we can write that now as A plus mod squared minus A minus mod squared of A plus mod squared, but we've got A minus mod squared from that expression at the top, and as a multiple of A plus mod squared, so we can write this as 1 minus q minus 1 over q plus 1 mod squared. Well, the mod square of this ratio is the ratio of the mod squares of the top and the bottom. So this can be written as 1 minus q minus 1 mod square over q plus 1 mod square. So let's address ourselves to what these mod squares are. So what's q minus 1? Well, q minus 1 is going to be, well, it'll obviously, on the top, it will have the existing top minus the bottom. So when we take away the bottom from the top, the Cauchys go away, and we are left with, I think, k over ik minus ik over k times sine 2ka. And that will be over, I'll just call it the bottom because we're not really going to take much interest in what this bottom is. It is the bottom that you see up there, cosh 2ka minus k over ik, etc. And q plus 1, the reason we won't care about the bottom is, of course, it will cancel when we take this ratio. So for q plus 1, we unfortunately find that the Cauchys add and the shines irritatingly refuse to cancel. So this becomes 2 cosh 2ka. We're adding, so we have minus ik over k plus k over ik, all in a bracket, sine 2ka. And again, that's over the bottom. So what we need to do now is take the mod square of these two numbers, ratio them, and take it from 1. So the fraction that gets through is going to be 1 minus so the top of that is completely imaginary, right? It's pure imaginary. We should take out an I from that bracket, and then we will find we're staring at k over k plus k over k squared times shine squared 2ka. So that's q minus 1 mod squared as regards the top. The bottom we're not interested in because they're going to cancel with the other bottom. And now we have to put underneath the mod square of this, which will be 4 cosh squared 2ka, right, because this is the real part of it, this is the imaginary part of it. We take out a factor I, and now we're staring at plus k over k minus k over k squared shine squared 2ka. Nearly there. So now we put these two bits, it'll simplify if we put these two bits on a common denominator. So the top, when it's on a common denominator, will be this bottom plus that stuff there. So this will be 4 cosh squared 2ka. And now we're going to have shine squared, let's write it in, plus, yeah, shine squared 2ka, brackets. Now, brackets what? We will have this bracket squared, well, we'll have this bracket squared, sorry, minus this bracket squared. And when we square these brackets, we're going to get k squareds over k squareds, which will cancel because of that minus sign. And what will not go away is the mixed term, the product of multiplying this on this, which generates 2, and the product of multiplying this on this, which generates another 2. So we will get 4, and it will in fact be with a minus sign, because this minus sign is there. You know, when this comes up here, that minus sign will stick out, and this minus sign will make the mixed term minus there. So this is going to be times minus 4, and it's over the bottom as you see it, over 4 cosh squared 2ka plus k over k minus k over k squared shine squared 2ka. And the top simplifies most beautifully because cosh squared minus shine squared is 1. So the 4's can be cancelled, and this actually is nothing but 1 over. So the fraction is 1 over cosh squared 2ka plus a quarter of k over k minus k over k squared shine squared 2ka. Not much fun. So what do we learn from this? What we learn from this is most interestingly, is what happens if we have a high barrier and the particles are very short of energy to get through, all right? So K is a measure of the deficit in energy that the particles, right, that they have, by how much they don't have enough energy classically to get through the barrier. If the barrier is very high and they don't have much energy, then we're looking at the cosh of a largish number and the shine of a largish number. And so what we can say is that for large Ka, we can say that cosh 2Ka behaves pretty much like shine 2Ka behaves like e to the 2Ka, right? But we are interested, in fact, in cosh squared and shine squared, so F is looking like 1 over e to the 4 Ka. So if Ka is an appreciable number, this probability of penetration is becoming small. The crucial result is that the probability of getting through there is decreasing exponentially fast in the height of the barrier. So you don't need a very high barrier to make this quite a small effect. And somewhere here we have, so this is, woohoo. This machine goes to sleep, doesn't it? That's the trouble. It shouldn't go to sleep. Give up. Is there anything there? I'll just draw it. Is it sort of? Yeah. No doubt we're saving the planet by having the machine turn itself off, but yeah, okay. I can't see it. So what you want to do some, so that's sort of asymptotically what happens when Ka is very large. In detail, you might want to know for smaller Ka, sorry. Right, so these results are for a barrier which is, so in these results, the barrier is not terribly high. So we have that V0, we have that E is equal to 0.7 V0. No. Sorry, what have I done? What have I done? Yeah, no, that is correct. Sorry. Yeah, the height of the barrier is, sorry. There's this parameter W, isn't there, which we talked about yesterday, which is a measure of the width and the height of the parameter, of the barrier. So it's 2m V0 A squared over h bar, this animal, right? That's your dimensionless measure of the height and the width of the barrier in terms of the mass of the particle with no reference to the energy of the particle. Sorry, that's not the case. Then what's being plotted here is the probability of getting through as a function of your energy over V0 for barriers of different Ws. So I think, is it a 0.5 at the top there? Yeah, so here's a relatively weak barrier which gives you at fairly small energies a chance of getting through. In other words, it's not a very fat barrier, that's the crucial thing. This is a fatter barrier, this is a fatter barrier, and so you can see how, as a function of the energy, your chance of getting through rises in detail. Okay. See if we can get these things to stay alive for later. What's physically interesting about this, or an interesting application of this, is the radioactive decay. So this is obviously a very simple-minded model that we have so far, but the general idea, for example, is this. So what we should say is that inside 238 uranium, which is the non-fissile sort of uranium, you have a number of alpha particles. This is a simple-minded picture. So what does the potential energy of an alpha particle, so we kind of consider this to be, so 238 uranium, which decays to 234 thorium, and an alpha particle with a half-life of, I think it's 6.4 gigayears. Right? So it takes the age of the universe, typically for a uranium-238 made in some supernova, to eject an alpha particle. So what's happening here from this perspective? What's happening? So what we should do is we should think about this alpha particle and this uranium-234 nucleus as a kind of dynamical system. So the alpha particle when it's a long way from when it's a decent distance, more than 10 to the minus 15 meters or so, away from the thorium nucleus is repelled by the electrostatic repulsion. So the potential energy curve has a sort of 1 over r type behavior here. When it gets close enough to the thorium nucleus, the strong interaction, it's able to exchange gluons and stuff with the alpha particles, with the nucleons inside there, and it feels an attraction. So there is a well that looks a bit like this, except this is extremely narrow. So the width of this, right, is say 10 to the minus 15 meters, sort of typical nucleus size. So inside that uranium-238 that you mine in Australia or something, there's some alpha particle moving around in here with a large velocity, a sort of relativistic velocity. Every motion inside nuclei is kind of relativistic. So it bangs to and fro across here, right? If you've got 10 to the minus 15 meters to cover and you're traveling at some speed comparable to the speed of light, that means that you cross this thing, what does this give me? 10 to the minus 23, you need about 10 to the minus 23 seconds to cross. So roughly 10 to the 23 times a second, this alpha particle bangs to and fro, to and fro, to and fro. This will be the classical picture. And it needs to do this, so it does this for on the order of 6.4 gigayears, so for many gigayears. So for on the order of, shall we say, 10 to the 17 seconds, which is a third of the age of the universe. So it makes about 10 to the 40 impacts on the barrier. And then, wonderful moment, it gets out on the 10 to the 40th attack, whatever. It slips through here and goes off to infinity. So this astonishing phenomenon of systems with incredibly small dynamical times, the smallest dynamical times in the typical physical world, doing something on a timescale which is the age of the universe. It is the most astonishing phenomenon, but how does it happen? It happens through this exponential decay. The height and width of this barrier are substantial, but that e to the 4, there's that e to the 4 times the height and width of the barrier amplifies this so much that your chance of getting out turns out to be only 1 in 10 to the 40. So that a neutron that got trapped in there in a supernova before the sun was born pops out today. So we should now, so that's the end of games with square potential wells. I hope you get the idea that it's a rather artificial, it's a scheme for finding solutions to the time-independent Schrödinger equation, which can illustrate interesting physical phenomena, although the potentials themselves are very artificial. And we should now just ask ourselves, what of the results that we've obtained would be spoiled, would change if the changes in potential weren't abrupt, right? In the real world, they're not going to be just step potentials. We've used step potentials as a computational convenience. In the real world, they're going to have to extend over some distance, and one wants to understand, it's important to understand which of these results would survive and which would be spoiled by taking a more realistic potential. And I've focused on problems where stuff would survive and tried to neglect problems, or haven't spoken about problems which would be seriously damaged, but you can be misled. So in particular, if we would do a calculation precisely analogous to this for particles encountering a square potential well, all this calculation could be pushed through with the minor modification that in here we would have b plus e to the I kx and b minus e to the minus I kx, big kx, right? We would have two. So if we had particles moving in here from infinity with an energy greater than 0, the particles, when they got here, would speed up and slow down when they got here and stuff, and classically all the particles would pass through. If you solve this problem using this apparatus here, what you're going to find is that some of the particles are reflected from this barrier. Well, some of the particles are reflected, from the whole setup. I don't want to say which barrier they're reflected from, because there are two barriers they can be reflected from, and the results are a superposition of those, and some particles get through. And if you do this calculation, you are learning something which will be profoundly changed if you're more realistic and say, well, my real potential well, of course, is going to have somewhat slopey boundaries. And the issue is, how steep does something have to be for this to be a decent guide? The good news is that the results to that kind of calculation are not going to be profoundly affected by the steepness. They'll be somewhat affected, but not enormously affected, so long as we stick. We would be misled if we put particles in at sufficient energy that they were classically able to get over the top. But if we stick to particles which are classically forbidden in here, we're not going to be enormously deceived by taking sharp boundaries. How do we do this? Well, what you need to do is numerically solve the solve the wave equation, solve the time-independent Schrödinger equation for some kind of a potential change which can be made either steep or less steep. So if you take that the potential as a function of x is equal to some constant brackets times naught if x is less than minus a, and in this zone here is something like 1 plus sine pi x over a. That's for mod x less than a, and you take it to a 1 down here if x is greater than a. I hope I've done that the way I should have done that. Then you will, so this is just a simple functional form that describes a curve that looks like this, right? It goes from v naught here, it's precisely v naught when you're more than a away, and it's precisely 0 if you're to the left of minus a, and it moves smoothly and continuously with a continuous gradient from one thing to the other thing. And by changing a, you can make this steeper or less steep. And it's very straightforward. I urge you to try it on your laptop. To solve the time-independent Schrödinger equation numerically, there's a problem describing how to do it, I think, certainly in the book, possibly in a problem set. And what do you find when you do it? You get this kind of curve here. So this is the reflection probability as a function of Ka. That's right. And this was what I did for an energy E, which was equal to 0.7 V0. So all of these solutions are for energy E equals 0.7 V0, which in the square, if we have an abrupt, sudden change in the potential, gives us this probability of roughly 0.1 of being reflected. Sorry, this is the probability of reflection. Did I say something different? This is the probability of reflection, and the square one gives you, the sharp one gives you this. The numerics reproduce this if you take Ka, and A is now this, not the width of a well, but the width of the transition. Well, 2A really is the width of the transition. If Ka is less than 1, then the numerics reproduce the analytic solution. But if Ka is bigger than 1, you see there's look at this as a logarithmic scale, right? This is a probability of 0.1, 0.01, 0.001. So the probability of reflection drops like a stone as Ka becomes bigger than 1. So the abrupt transition is going to be profoundly misleading unless the transition, so the step, in this case where we have, what's crucial here is that we have a transition from between two zones within which the particle is classically allowed, right? So the step between classically allowed regions is misleading. It exaggerates reflection if Ka is greater than on the order of 1. That is to say, what does that tell me? K is 2 pi over lambda, so that tells me that if A, the transition width, is greater than 2 pi over the de Broglie wavelength, right? So the transition really has to be quite abrupt in terms of this natural sense of scale. If you ask, so what's the de Broglie wavelength for an electron? The answer is that it is on the order of 1.2 times 10 to the minus 9 energy over 1 eV to the half meters. So the de Broglie wavelength, this quantity for an electron, and because I mentioned electrons obviously because they're things that we do fire around our laboratories. People used to fire them around their homes even when they had cathode ray tubes. So it's a typical kind of particle you want to understand about. Then the de Broglie wavelength is a nanometer or so times the energy in electron volts. Oop, that's a minus a half, isn't it? Because the higher the energy, the shorter the de Broglie wavelength. So if you are constructing a step potential, typically you are going to be doing it by having some kind of doing some kind of solid state physics, so that those sheets of glass provide pretty much a step change. They provide a change in the refractive index, which affects photons, right? So photons hitting the window have a chance of being reflected, a chance of being transmitted, basically as if it were being bounced off a step potential. Why? Because the photons have wavelengths, those photons that we're bouncing off the windows have wavelengths of 500 nanometers or something. And atoms, so the size of an atom is, of course, on the order of 0.1 nanometers. So it's easy using atoms to make changes that occur over a few atoms, therefore over on the order of a nanometer. So you can make, if you are using atoms to make the barrier, you're propagating your electrons through some kind of solid state material, you can probably make a step change which has you can change the effective potential the electron experiences within on the order of a nanometer. So you may be able to get useful results out of this, provided your energies are lower than 1 eV. But that's extremely challenging. In practice, your energies will typically be higher than 1 eV. So these results are going to be basically misleading. What you see here is a return of common sense and rationality. If you roll a piece of chalk off the edge of this table, it will of course fall. It won't be reflected. It's not going to be reflected by the lower potential, the onset of lower potential. And that's what the numerics are saying here, that unless you have that in practice, when something encounters a drop in potential, for example, the reflection chance is going to be, in fact, very small, because this is not going to be abrupt. It's going to be like this, a tiny bit easy, and then everything is basically going to get through. So what actually happens is that when you have a slow change, a gradual change in the potential, is that the wavelength, as the electron or the particle comes along, it comes to this region of lower potential energy. We would say it speeds up. The numerics will show you that the wavelength of the wave is getting shorter, so the momentum is getting larger, because as p is h bar k, yes, it's speeding up, and it's just there's no reflected wave, so the whole thing just moves into a new regime with a shorter wavelength, everything changing continuously. Well, I think that's pretty much all I want to say, so we'll finish there, and that's the end of step potentials, and on Monday we can start on